Imagine yourself sitting comfortably inside a train, its engine roaring as it races down the tracks at nearly the speed of light. You glance out the window and notice something peculiar. The world outside seems to move in slow motion, as if time itself is stretching and swaying. Yet inside your train car, everything is just as it's always been. Your watch ticks away. Your heart beats steadily, and your thoughts flow in their usual rhythm. Bizarre? Absolutely. But this isn't the stuff of science fiction. This is reality, as described by one of history's greatest minds, Albert Einstein. Prepare to embark on a journey that will illuminate how time can slow, space can bend, and how a curious young patent clerk forever changed our understanding of the universe. Albert Einstein was born in 1879 in the quiet German town of Ulm. From a young age, Albert was different. While other children followed their teachers' instructions without question, Einstein was a relentless questioner, always probing, always seeking to understand why things worked the way they did. He quickly grew frustrated with the rigid, authoritarian methods of his schoolmasters. For young Albert, true learning happened at home, hunched over stacks of books, lost in the pages of science texts. By the age of 12, he was already devouring works on Euclidean geometry, not out of necessity, but out of a deep and genuine pleasure, a nearly spiritual fascination with the patterns and logic of the universe. Of course, such independent thinking brought its own set of challenges. Einstein's refusal to memorize facts or accept ideas without reason led to conflicts with teachers and difficulties in school. But his struggles were never due to a lack of intelligence. Rather, they stemmed from his refusal to accept rote learning or arbitrary rules. Eventually, his family relocated to Switzerland, where he enrolled at the Polytechnic School in Zurich. Not every subject captured his imagination, but in mathematics and physics, he stood out. He graduated in 1900, but even with his obvious talents, securing a job in academia proved elusive. For several years, Einstein drifted, taking odd teaching jobs and feeling increasingly disillusioned with his prospects. That's when the young physicist found work at the Swiss Patent Office in Bern. His days were spent reviewing applications, but his mind soared elsewhere. Each evening, after hours of routine paperwork, Einstein would retreat to the quiet corners of local, his notebooks filling with equations, sketches, and wild ideas about the nature of reality. Then, in 1905, a year now known as his miraculous year, Einstein published 4 groundbreaking scientific papers. Among them was a radical new way of thinking about time and space, the special theory of relativity. Up until Einstein, time was seen as an absolute universal constant. The clock ticked the same everywhere, at every moment, for everyone. At least, that's what Isaac Newton had assumed. But Einstein dared to ask, what if the flow of time depended on how fast you were moving? What if time was not fixed, but elastic, stretching and contracting depending on your motion? This idea, known as time dilation, was one of the most astonishing revelations in the history of science. If time could stretch, then so could space. Einstein realized that space and time were not separate entities, but two sides of the same cosmic coin, a single, four-dimensional fabric he called space-time, move faster. And not only does time slow down for you, but distances contract as well. Suddenly, the universe was no longer a static stage where events played out, but a dynamic, malleable arena where space and time could bend, twist, and fold. At the heart of Einstein's special relativity lies one unshakable rule. The speed of light in a vacuum is always the same, no matter how fast you're moving. This constancy is deeply counterintuitive. Imagine shining a flashlight while sitting still. Then again, while racing in a car, the light should move faster relative to the ground, right? Not so, according to Einstein. The velocity of light remains fixed, and it's space and time themselves that adjust to compensate. This insight led to the most famous equation in all of physics, E equals mc squared. This deceptively simple formula reveals that energy and mass are interchangeable. A tiny amount of matter can become an enormous burst of energy, and vice versa. It's the equation that powers the sun's brilliance and, in humankind's hands, both the promise and peril of nuclear energy. Consider one of the most mind-bending consequences of relativity, the twin paradox. Picture two identical twins. One remains on Earth, while the other embarks on a journey through space at a speed approaching that of light. Upon the spacefaring twin's return, he finds that he has aged more slowly than his sibling on Earth. This isn't a mere thought experiment. Time dilation is a measurable, real phenomenon, and its effects have been observed in high-speed particles and in astronauts orbiting our planet. Still, Einstein's special relativity had its limits. It worked beautifully for objects moving in straight lines at constant speeds, but it couldn't explain the force that holds planets in orbit or causes apples to fall from trees' gravity. To tackle this, Einstein spent a decade wrestling with deeper questions, eventually unveiling his masterpiece, the general theory of relativity, in 1915. Here, Einstein proposed a breathtakingly new vision of gravity. Gravity, he said, is not a mysterious force pulling objects together across space. Instead, it's the very fabric of space-time curving in response to mass and energy. Massive objects, like planets and stars, warp the space around them, creating dips and curves. Smaller objects follow these curves, giving the appearance of gravitational attraction. Imagine a bowling ball placed on a stretched rubber sheet. It creates a depression, and a marble placed nearby will roll toward it, not because of some invisible pull, but because the sheet itself is curved. This concept, though difficult to visualize, was put to a dramatic test in 1919. During a solar eclipse, teams of astronomers from Britain and Brazil observed the positions of distant stars whose light passed close to the Sun. As predicted by Einstein's equations, the Sun's gravity bent the starlight, shifting the stars' apparent positions in the sky. The results were clear. Einstein's theory was right. His fame exploded overnight, and he became a household name across the globe. Relativity isn't just an academic curiosity, it's woven into the fabric of our daily lives. Take the GPS satellites orbiting above the Earth. Their clocks tick at a different rate than clocks on the ground, thanks to both their high speeds and their distance from Earth's gravity. Without the corrections provided by Einstein's theories, GPS systems would accumulate errors of several kilometers in just a single day, rendering them useless for navigation. The closer you are to a massive object, the slower time moves for you. In the realms near a black hole, time can slow to a crawl compared to a distant observer. This isn't science fiction. Astronomers have measured such effects, and the concept was vividly depicted in the film Interstellar, where minutes near a black hole translated to years elsewhere. Even light, which travels at the ultimate speed limit, isn't immune to gravity's influence. Light passing near massive objects can be bent, magnified, and split, creating phenomena known as gravitational lenses. Astronomers use these cosmic magnifying glasses to peer deeper into the universe, observing galaxies and explosions billions of light-years away. Einstein also predicted that violent events in the universe, like the collision of black holes, would send ripples through space-time itself, known as gravitational waves. For a century, these waves were elusive, but in 2016, scientists at LIGO finally detected them, confirming that the universe can indeed ring like a giant cosmic drum. Einstein was deeply invested in the concept of causality, the idea that events are linked by clear causes and effects. This belief put him at odds with the emerging field of quantum mechanics, which seemed to suggest that the universe is governed By probabilities and randomness, God does not play dice with the universe, Einstein famously insisted, yet the evidence for quantum randomness continued to mount, challenging even his formidable intellect. In Einstein's vision, space is not an empty stage. It is dynamic, alive, and responsive, shaping itself around the matter and energy it contains. The universe doesn't merely exist within space, it is the very tapestry of space itself, ever-changing and interconnected. For Einstein, beauty and simplicity were guiding principles. He believed the laws of nature should be elegant, revealing deep symmetries and patterns. His equations, though challenging to master, have a mathematical grace that continues to inspire physicists to this day. Understanding relativity isn't easy. It requires letting go of some of our most basic intuitions about time and space. But with curiosity and the right analogies, anyone can begin to grasp its core ideas. As Einstein himself said, if you can't explain it simply, you don't understand it well enough. The story of relativity is not over. New discoveries, spinning black holes, dark matter, the accelerating expansion of the universe continue to test its boundaries. While relativity remains one of the most successful theories in science, it may not be the universe's final secret. And so, questions linger. Why did Einstein resist the weirdness of quantum mechanics? What drove him to search for a unified theory of everything until his last days? How did the cosmological constant, a term he once called his biggest blunder, come roaring back as the mysterious dark energy? These puzzles, and many more, await the next generation of curious minds. If you've enjoyed this journey through time, space, and the brilliance of Einstein, consider joining the curious order. Here, curiosity fuels intelligence, and knowledge is our greatest reward. Thank you for traveling with us. Until next time, keep wondering, keep questioning, and continue exploring the incredible mysteries of our universe.